begin this seminar. Today we have the pleasure to have Andrea Braides, who will speak of topological singularities in periodic media. And he's a professor at the University of Rome Tor Vergata, Sottodetta Roma 2, e al momento per questo anno è in residenza alla SISA a Trieste. Andrea, go on.
Thank you very much. So it's a pleasure to be at least virtually back in Paris. It's been a long time since I have spoken in this seminar, so it's really good to be back here. So as François mentioned, I'm going to talk about some work together with Roberto Ricandro, Marco Ciccarese, Gianluca, and Andrea on homogenization and singularities. So this is a work that has had a lot of different motivations. So we started thinking about this work when looking at the homogenization for energies defined on functions with values in manifolds. And somehow the sphere is the easiest manifold, even though we are thinking of oscillating manifolds. And on the other hand, another motivation is a theory of perturbations for the Ginsburg-Landau energy. Somehow, this is why we have a lot of people in this work, because we were looking at these two different. There were two teams looking at different aspects, and then we joined forces. And now today I'm going to talk about the result. So I have to talk a little about the Ginsburg-Landau energy, even though this is very well known, especially in Paris. So we have omega, an open bounded regular sets in R2, connected, say, and we want to look at minimum points, minimizers of an energy which can think of being a perturbation of a lower energy. So we can write this here, squared dx plus a small perturbation of a gradient term, dx. Now I put this also a coefficient, because then I will play with this coefficient, and where u is from omega to values in R2. And we have a boundary condition, u0, which is non-trivial in the sense that the degree of u0 is on the boundary, is some positive integer, different from 0 then. So we have something with non-trivial degree as boundary data. So if we look at this problem here, so we think of having this omega set, and this is our non-trivial datum u0 that we can picture something like this. This is u0 on the boundary, and we want to match this boundary datum here, and we want to know what happens as epsilon goes to 0. Now, as epsilon goes to 0, you see this is a lower order term, so we expect minimizer just to have modulus 1. So we would like the minimizer to be of modulus 1, and all the minimizer at epsilon scale, they are in H1. So in the limit, we would like something in H1 with values in S1, but this is incompatible with the degree. So what happens is that if you look at minimizers, we will have formation points, formation of vortices. So we will have some points such that the limit function, say, will be will have a non-trivial behavior at these points. So we look like something which is not H1. So the limit problem, then we have as epsilon goes to zero is the formation, is driven by the formation of topological singularities, which are vortices. This is a very well-known theory. I should quote a lot of people, but I'm not an expert in this field. So I go the classics. So Betuel, Braides, Laine, Sambier, Gerard and Sonner. So these are always quoted as describing this very rich problem as epsilon goes to zero. Okay, I'm not going to specify well as the topology in which the minimizer converges to vortices, because it's not interesting, it's not essential to what we are going to describe. So, if we want to look at an energetical formulation for this, we have to use the right energy scale. So the energy scaling, well, loosely speaking, okay, take U epsilon, which is equal. So suppose you have one of these vortices, which we call xi, okay, around which we have some topological singularity. Suppose then we can test one function which has the form x over xi, well maybe x over modulus of the size outside the ball of center xi and radius epsilon. Okay. So these are in S1, so outside this ball, this is negligible, so we have a contribution which is over epsilon squared from this part. If you look at this part, you have something, the gradient is grows like 1 over the distance. So you have 1 over the distance squared, then you integrate with respect to with respect to the distance, you have some Jacobian determinant, and you see this goes like a logarithm of epsilon. So this for this, the gradient of u epsilon, say dx on omega, goes like a logarithm of epsilon in modulus. So the right scaling in which you can see this energy will be maybe finite is by dividing so that this part is finite, say divided by epsilon squared log epsilon. So the energy scaling here we can write in this form, log epsilon in front of everything, and here we have we divide by epsilon squared.
Andrea?
Yes?
Excuse me, this is gradient to epsilon squared.
Above.
Above?
On top right.
Oh yes, it's squared. Sorry, this part here. Thank you. Okay, and these are the Ginzburg-Landau energies of U at the scaling, at the vortex scale. So with this in mind, we see that these energies, well, these in a sense of gamma convergence, they concentrate on. So if U epsilon, say, tends to some set of has some vortices, in general, we will have some gamma convergence to something which is 2 pi a, say, and then we have the sum of di, and then here we have the sum of I, where di is the vortex index. So it says that the minimizers, in a sense, we'd like to minimize this set. Okay, we will have this energy, and that's the location of the minimizer is obtained by minimizing again an higher order energy, which is called the renormalization energy. But we are going to focus on this passage to the limit. And we are going to make a perturbation. And this perturbation is a classical homogenization perturbation in which we take a periodic function and we perturb this part with this periodic say coefficient in front of the gradient. So this means that we are looking at an inhomogeneous medium in which this perturbation may depend on the point, and for the simplicity we have that A is the periodic function between two constants, and so A is one periodic, and so we have something which depends also on the scale delta, and we have epsilon and delta that goes to zero. Now, actually, for the time being, since I want to make some computations, I look at very special A, which is the checkerboard function. So we have something which in the unit cube, in the unit square, we are in 2 dimensions, has 2 values, alpha and beta. And then it is extended periodically. So it's a checkerboard coefficient. This is a simple coefficient, meaning that we have a lot of symmetries, and we expect that this, if delta goes to 0, maybe we have some simplifying symmetries. Okay, so the question now, what is this scaling the energy of a vortex? And then also, what is the dependence on epsilon and delta? So somehow these are the questions that we would like to address and to solve. So the heuristics, this is a classical, looks at least like a classical scale separation, multiple scale problem, if you want. So the heuristics, well, you have 2 scales, and maybe we have a simplifying behavior if one scale behaves in an extreme way with respect to the other one. So, so if delta is oscillating very much, so if this is a very fast oscillating energy, so if delta is much smaller, well, of some scale of epsilon. So if delta is very small, so we don't know which scale is this one, then we expect this energy here to behave like a homogeneous energy. Actually, there is a little caution here, because here this is a vector values function. So to compute this, to use the classical scalar value homogenization, you have to be a little careful. But if we are in 2 dimensions, so you can write u in terms of an angle variable here, more or less, except some variation, because you are close to S1, is more or less like like ELI to the IP, and then this in this case behaves like exactly like gradient of phi squared dx. So phi is a scalar variable, and we know that the energies of this form can be homogenized in the sense that minimum problem with given Weinberg data related to these energies converge to the limit homogenized energy. And in this case, this homogenized energy, so the idea is that this behaves like homogeneous energy, which we can look up in classical books. It's square root of alpha beta integral square dx. So if you are in a regime where delta is very small, then you are in this regime with alpha with this a constant, and it's a square root of alpha beta. Instead, if delta is much larger than, so the oscillations in delta are very large, so that you can suppose that functions are more or less smooth around points. So this coefficient is smooth around points of where you have concentration. Then, so x over delta will be close to its concentration point. You will have some values for this. So you will near some singularity. You will have up to so x over delta will converge. So this will be xi over delta will converge to some y modulus 1. So this energy here, you will excuse if I erase something like this. So it will behave like having a constant here, because everything will happen close to a singularity. So this will be very close to a constant. So some epsilon or some y, some a or some y, the integral. So again, you have something concentrating on the singularity. So this will be close to some singularity. So will be something on some y, which is the singularity, something when scale converges to the singularity. So we can optimize this value here because we are minimizing. And in order to optimize, you have something like the mean of A, which in this case is just alpha. So in the extreme cases, you have that if this behaves like having a fixed coefficient, but in one case is square root of alpha beta, in the other case is just alpha. Okay, that's good. We have some heuristics then, and well, I'm erasing this energy and I will rewrite this immediately because I want to compare this result with the gradient theory with the, say, in Italy we say modica mortola version. So the gradient theory of phase transition. In this case, the scale is different. So we have some modica mortola, let's say, energy. And these are, well, in this case, you have, so for phase transition, U is with values in R. So the difference is that for phase transition, you have a scalar variable. And for scalar variables, so we can rewrite something again, this. But the right scale is not epsilon squared log epsilon, but it's just divided by epsilon. So in this case, it's easy to understand what is the scale here. These two scales are just epsilon. So in this case, S plus, S minus is just the scale epsilon. And if, well, if delta is much less than epsilon, so we know that this will give rise to sharp interfaces, to perimeters. So in the end, we will have zones where you have on one side u equals 1, on the other side u equals -1. So you epsilon more or less 1 and you epsilon -1. And then you have an interface here. And then we look at the cross section. So if delta is much lower than epsilon, then looking at this cross section, we go, well, let's say we go from -1 to 1. So oscillation will be very fast. So you will have an interface like this, which superposes to very fine oscillations. If delta is much larger than epsilon, then you have very large oscillations. And then you place the interface where it's more convenient. If delta is equal to epsilon, then the picture is more or less like this, but then you understand that these oscillations also can interfere with the shape of the transition. So this is the case for the gradient theory of phase transition. So the answer is, okay, you have two scales, and the behavior of the limit depends essentially on delta over epsilon. If delta over epsilon tends to 0, then you're in this case, which means that you first homogenize and then you make the phase transition. If delta over epsilon goes to plus infinity, you are in this case in which you first compute the phase transition energy and then you homogenize. Otherwise, the two processes act on the same scale. So we have this result in mind, which, by the way, I have to quote, was obtained a long time ago, together with Nadia Ansini and Valeria. So now we go back to our energy, and we have to go a little technical. I have to say that all the technical points on the Ginsburg-Landau part I have viewed to my co-authors, and so if you ask questions about this, you will put me in difficulty, but I want to describe anyhow what happens. So we do a first simplification. Which says that we can actually remove the first part, the part where you have the square minus 1 over epsilon squared, and replace it by a sharp condition, so to be with values in S1. Of course, this is in contrast with the requirement of being in H1, so you have to do something. And the Correnius approach goes like this, that we have a lemma, if you want. The behavior, I will state this vaguely, but meaning that the gamma limits and the minimum problems have the same behavior of this Ginsburg-Landau with epsilon delta is, well, you could put also an A here, is the same as some functional, which I'm going to describe now. These functionals, depending again on epsilon and delta, the final functions u, and on points xi, on a number of points, a finite number of points xi, and are simply given by the integral of omega minus some balls of radius, is called radius epsilon, center in xi of a of x over delta gradient u squared dx. And u is in h1 omega minus this union of balls with values in s1. So we have simplified our energy, removing the first part, but adding a constraint. The functions are already with values in S1. So the picture we have in mind, and this xi are also the variable of our problems, and are the points that we tend to vortices. So we have some points around which we remove some little balls of radius epsilon, and the function is in h1 outside. Of course, it will be convenient to introduce these vortices, these points, if we have a non-trivial degree on the boundary of these points. Otherwise, it's not good. And so we can use these energies to give an estimate, and these energies somehow are easier to look at, to handle, because you don't have to cope with the first term, and this has a very precise scaling behavior. So what we do, we want to understand what is the contribution of something like this, of a function which has some non-trivial degree around on the boundary of a ball of radius epsilon around the point. So we isolate this point. Maybe it's easier to write it here. So we isolate one of these balls from the others, and we try to estimate what happens on each of these larger balls which separate the contribution of the vortices. So we compute a lower bound. To compute a lower bound, now here we only prescribe the degree here. So the thing that we have to look at, so sorry, there is something missing here, the scaling factor, 1 over log epsilon. So the lower bound, so we isolate what happens here, so we have to look at 1 over log epsilon, and then we minimize. To have a lower bound, we minimize on this larger ball, which we can always think of being of size 1, because everything scales logarithmically here, so the contribution, so that the gradient scales like 1 over the distance, and on a small, if we change it from a ball to a ball of another fixed radius, we obtain something which is negligible with respect to log epsilon. So on this, we can center a ball in 0. We can translate this problem in 0, and we have a of x over delta gradient, say v squared x, where the degree of v on the boundary of v epsilon is fixed. So we would like to compute something. We give a lower bound on problems of this form. Of course, we can then sum up the lower bounds and obtain a lower bound for the whole energy. Actually, it suffices to look at the degree equal to 1. And the reasoning are the same, but I don't want to carry on with this D. So the degree is, we think of being 1. So as it is often the case in variational problems, a key point is the variation of the boundary datum. So when you, even in homogenization, it's very nice to pass from periodic, at least when you have asymptotic problems, to pass from periodic boundary conditions to fixed boundary conditions with Dirichlet data, and prove that that you can pass from one to the other without asymptotically missing anything in the end. So here we have some lemmas, some observation, which again I state vaguely, and I only recall that this is due to a technique introduced by Sandier, which called the ball construction, and which says, okay, in this problem, we will take the degree fixed, the degree also in B1, B1, or, which is better, since we have fixed degree 1, x over modulus of x, both on the inner ball and the outer ball, which is very convenient here. So you can vary this. Maybe in the beginning you don't have the degree 1, but then you can choose a slightly different radius so that the degree is 1, and then you can also vary the boundary datum so that it's exactly x over modulo x. So going from something which is degree fixed to something x modulo of x, which is degree 1, say it's negligible. You can do that with very little energy with respect to logarithms. Okay, and then we can make a little computation which says that, okay, in the case where you have constant, if A is constant, well, then this minimum, well, the minimum 1 over log epsilon, the minimum over B1 minus B epsilon of, well, let's put it A here, credit use B squared. Now we can put it B equal x over modulo of x on the boundary of B1 and the boundary of B epsilon. Then this is achieved exactly on x over modulus of x. And so you can compute it, it is 2 pi. More, if here instead, and of course you can having the ball 1 and epsilon, or radius 1 and epsilon is general, and so another thing that we want to remark, if here we have 2 scalings, epsilon to the gamma 1, epsilon to the gamma 2, then here you have gamma 2 minus gamma 1, 2 pi epsilon. Again, it's just a computation. You plug x over modulo x. So you realize that the minimum is the function x over modulus of x itself, and the energy is this one. Okay. Now, I think we can keep this in mind, and so I can erase this whole blackbird. We can go back to our minimum problem. So we want to estimate 1 over log epsilon, the minimum. I rewrite here the integral of v1 minus v epsilon, a of x over delta gradient v squared, dx dx over modulus of x on the boundary of v1 and the boundary of the epsilon. So I have to make a big picture here. We have scale 1, and then you have scale epsilon here. Now we want to introduce another scale. So the idea here is to introduce another scale around this inner ball, epsilon to the gamma. So so here we have epsilon. So introduce the epsilon to the gamma. So gamma is less or equal to 1. So this minimum we can estimate, or we can rewrite as 2 minima. Why 2 minima? Because here, without loss of generality, we can still vary the boundary condition with the value of v and put it equal to x over modulus of x. You can do this, okay, but up to varying a little this radius if really epsilon to the gamma does not work. So you can estimate separately what happens on, I should rewrite everything, well, yeah, I can. So we want to have 1 over log epsilon, and then the integral of v1. I'm not writing the minimum, so take a minimizer. So I take it on v1 minus v epsilon to the gamma, a for x over delta, gradient v squared dx, and then we have plus 1 of log epsilon, so you can minimize separately. I'm not writing the minimum problems because of reasons of space and time. Okay, so we can think of minimizing separately these two. So it's not a plus. We're minimizing separately these two problems, and then summing up, you give a lower bound of this minimum. Now, the idea is, okay, here we will be close to a point, to a vortex, and we would like to have the least possible energy close to this vortex. What to do? Place the vortex where you have alpha. So this is larger or equal if you put just alpha here. Now you're minimizing something that I have erased, but if you look at your notes, of course you have any notes, you see that this is the minimum of this gives exactly so 1 minus gamma times alpha 2 pi. So minimizing this with values x over modulus of x on the boundary gives this value here. So with this computation that we have organized before, it gives a lower bound. Now what about here? Now I can be sloppy or I can be precise. So if I am sloppy, I would say, okay, now I choose another, I give some other, this is always valid, whatever gamma is. Now I choose some scale gamma, so that here I have homogenization, which means that this scale's delta must be much smaller than the scale of the domain. So choose delta, choose gamma, such that this is delta is much smaller than the scale of the domain, which is larger than epsilon to the gamma. So if you choose delta much smaller than epsilon to the gamma, then this behaves like a homogenized. So we are computing a minimum problem with fixed boundary data, x over modulus of x, which is in H1. So we can replace this with square root of alpha beta. Of course, I'm cheating because the domain is changing. So there is a little, well, a nice remark on the scaling properties of these energies, which amounts then to subdivide this annulus here in annuli in which the inner and the outer radius are all fixed with a fixed proportion, with this proportion. Then one of these radii will carry less energy than the whole. It will have an average which is less than the whole energy in this annulus. And you apply this homogenization technique to that annuli with boundary data x over modulus of x, and use the scaling properties of the gradient in 2 dimensions, which is invariant by so it's the minimum problem are invariant by scale. So somehow this sloppy argument can be made rigorous by choosing some other annuli in which the inner and outer radius have a fixed ratio. So this, if you minimize this, again you have gamma. You have epsilon to the 0, epsilon to the gamma. You're using the observation that we made before with gamma 2 equals gamma and gamma 1 equals 0. You have gamma square root of alpha beta 2 pi. So we have a lower bound, which goes like this, is larger or equal than 1 minus gamma, well, 2 pi everywhere, and then it's 1 minus gamma alpha plus square root of alpha beta. And this is valid whenever gamma is less than 1, and epsilon to the gamma is, well, epsilon to the gamma is much smaller, much larger than delta, which means that gamma, let me erase this, must be also less than, so it's less than the minimum, 1, and this is logarithm of delta over logarithm of epsilon. So the condition, this is the condition that epsilon to the gamma is much larger than delta. Now, you can suppose that this is fixed, so this converges. Up to subsequences, this converges to some lambda, which is in 0. Okay, and then the optimization here, because the larger you get, you have gamma, the nicer is the lower bound, then this is optimized by taking here. So this is the optimal lower bound using this separation of scale approach. And is this a good upper bound? Well, now we are we want to show how to construct an optimal, but I'm going to redraw this, how to draw an optimal sequence for a fixed vortex. So we have, I blow up a little close to some part of the checkerboard, and I place my center exactly at the center of an alpha cube, alpha square. Okay. Oh, maybe it's too small, this alpha square. I draw it larger. So I put it in the center of an alpha square. In the center, inside an alpha square, doesn't matter. And then I choose gamma 1, say, and gamma 2, such that, let me see, so you have here epsilon to the gamma 2, which must be less or equal than delta, but let's say also delta, and then you have some epsilon gamma 1, which is much larger than delta. But we require that due to this condition here, then gamma 1 and gamma 2 are very close. Gamma 1 is lambda plus some little or minus some little 1, and gamma 1 is lambda plus little 1. So we construct the recovery sequence. So optimal sequence for a vortex of U1. Is obtained like this. Take well, u of x or u epsilon of x equals to x minus, so this is x0 minus x0 over x modulus of x. Of course, this x0 varies with epsilon, with delta. For x minus x0 less than epsilon to the gamma 1. So in this whole big disk, and then take a minimizer for the homogenization problem on with boundary data x minus x0 over x minus x0 on, say, v1 minus the epsilon gamma. So we have already seen that this gives the optimal, this gives a lower bound, except for this annulus here. So the computation gives the correct answer, except for what happens on this annulus here, which I can draw only taking a few cells, but this instead takes a lot of cells. But still, it's between the scale epsilon to the gamma 1 and epsilon to the gamma 2. And we can estimate this contribution. So the contribution of this annulus is less than taking just beta as a coefficient. So 2 pi beta So in the computation we had before, we were computing the minimum with the x over modulus of x. And here it's exactly x over modulus of x, which is the minimum, is 2 pi beta gamma 2 minus gamma 1. But we have chosen gamma 2 minus gamma 1 arbitrarily. We can choose them arbitrarily close to lambda. And so this is a little arbitrarily small. So this proves that this is a correct way to define an optimal sequence for a vortex. Of course, here we have chosen as set bolus values 1, but you can concentrate this construction close to each vortex and then patch up the construction. This is a standard in this kind of problem. So we have computed the energy of a vortex. So as a consequence, we have given the answer. So the energy of a vortex is 2 pi. Then we have 1 minus lambda. What's 1 minus lambda? Lambda alpha plus lambda square root of alpha beta, where lambda is the limit as epsilon goes to 0, or the minimum between 1 and log delta. Delta depends on epsilon, of course, dividing the log epsilon. And optimal sequences mix the two extreme behavior. So we don't have a single behavior depending on the way epsilon and delta, on epsilon and delta mutual way of tending to 0. We always mix the two extremes, of course, except at the cases lambda 0, 1, which are the two cases in which you have an extremely fast oscillations of the coefficients, or you have an extreme fast decays of the parameter epsilon. Except in the two extreme cases, then we have some optimal sequence which at larger scale oscillates, and then instead at a smaller scale close to the vortex, they behave just like x over modulus of x, and they don't feel the oscillations. Just one observation, that everything I have done was for this spatial energy, but just because the homogenization gives an isotropic matrix which is easy to compute. Otherwise, in the general case, instead of alpha, you have the essential minimum of A, and instead of square root of alpha beta, you have the square root of the determinant of the homogenized matrix, where this is the homogenized metric characterizing the gamma limit of that. So this is in the case of A, one periodic or periodic general. Okay, so I think that this is the for me unforeseen behavior, that you have two different behavior coexisting at the same time for this kind of homogenization problem. So you homogenize for at large distances, but then you don't feel that you optimize the location of the vortex, here in the minimum of A at close distance. Okay, I think my time is over. So thank you, Mark. Thank you very much for the attention.
Okay, thank you, Andrea, for this beautiful talk. I have to say that this is one of the first talk at distance that I can follow.
Thank you very much.
Probably, okay, evidently because you were great, but also because it's a domain of competence. Okay, so questions, maybe first in the physical audience. Okay, Antoine. Antoine Gloria.
Hi, Andrea.
Ciao.
I have two small questions, a bit related. It seems that you want to homogenize something with value in a manifold, but at the end of the day, you homogenize something which is standard, in the sense that it's only with the phi that you do something, and so that's because of 2D and of the fact that your coefficient is scalar, right? So my question would be, in 2D, can you handle a coefficient which would not be scalar, and can you do something in 3D?
So the coefficient, no, okay, you're thinking about this A. No, this you can generalize to a function which is too homogeneous in the gradient, but then you don't need to have a quadratic function. So that's that can be generalized. You know, that is not restricted. So somehow I wanted to do something which you can state easier. Of course, then you don't have the minimum, and you have to look at a more complex way to state this energy here. But somehow the principle is the same. Thank you for the first part, which is actually very interesting, and we were looking at a problem where the manifold is oscillating actually. So I have not mentioned that. So instead of having an oscillating an oscillating gradient term, you can look at an oscillation on the S1. Maybe you have oscillations on this one. That was done in very particular cases, but also in the scalar case, it's very complicated. So we tried something with Caterina Zeppieri, and the number of scales are there are crazy. So even for a very simple oscillating, so modica mortola energy. So when you have the wells are oscillating the modica mortola, even there you have a lot of problems, a lot of interesting actually scales that come up on the number of successive minimization problems that you have to solve. Yeah, that's very interesting. Of course, it would be very nice to have here something oscillating. Another thing would be to have a homogenization on something on a manifold which oscillates. I have done something with Valeria Chiedopiat, but for curves on something which has very wild oscillations. So something converging to a plane, but with a lot of oscillations, and there it's so the curves they wanted to follow the level lines, say, of this mountain. They don't want to climb them up and down this mountain. So you have say a minimal length problem to solve on. Fact is that you can. I don't want to give another talk, but somehow in this case you follow these level lines, but you can go also from one level line to the other one. So it's a nice problem to state. And instead, if you have functions with values in manifolds which are vectors, then again you can have much more interesting. For example, if these manifolds tend to concentrate on surfaces, even for the Dirichlet problem, you will end up with something which is defined only of functions which are polyconvex or quasi-convex, because they have to take into account some determinant constraint. That's very interesting, yes. But it's there is an enormous wealth of problems where the key is that the target is a manifold, you know, especially when it's oscillating. That's very, very nice to think about. Yes.
Thank you.
Okay, other questions in the room? No, so, okay, I propose now to the at distance participant to ask question if they want. Sorry. So I propose to distance participant to ask question now. So if you want to ask question, please raise a hand or open your microphone and speak. Okay. Apparently there is nobody who wants to ask question at distance. So I will ask a question in the meantime. So if I understand correctly, and probably I thought I understand correctly, you have two regimes. One where delta is less than epsilon. One when delta is much greater than epsilon. And you have the case where epsilon and delta have the same behavior. Or in other terms, log of delta or divided by log of epsilon tends to some lambda. Okay, so and in this scaling, you have a formula which is written on the blackboard: 2p1 minus lambda alpha plus lambda square root of alpha beta, which links the case lambda equals 1 to the case lambda equals 0, so the two previous states, to the two previous limits. Okay? No.
Yes, in this case, but it's not epsilon much smaller. Actually, it would be the case is lambda equals 0 and 1.
Yeah, yeah.
So,
sure.
Lambda equals 0 means that delta goes to 0 much faster. Goes to epsilon goes to 0 much faster than.
Okay, but this is exactly the case in usual homogenization, that you have two states and you pass from one state to another state to scaling, which is critical. Okay, quote the critical scaling.
Yes, the point here is that you have no critical scaling.
Yeah, the critical scaling is a limit of log of delta divided by log of epsilon.
No, meaning that at this energy, so this is a number. This is for example, take delta
like epsilon
equals it's 1. No, let's take delta epsilon squared. No, epsilon to the minus 1/2.
delta
Yeah.
epsilon.
So this is 1/2.
Yeah.
Okay. So this is 1/2. This says that at scales larger than 1/2, you have homogenization. At scales smaller than 1/2, which means very close to the vortex, you don't feel it's just the problem is where to place the vortex. Okay. Then you have exactly this scale, epsilon to 1/2.
Mm-hmm.
But a single scale for a Ginzburg-Landau problem has no energy at all. So it was a construction that I made in the small annulus connecting the 2 points. So you have oscillating functions far away, where delta is very small with respect to the scales. Then close to the vortex, you just place the vortex where the coefficient is constant, the least constant that you can, more or less. I mean, and then at the scale, exactly at the scale 1/2, say you take delta equals epsilon to minus 1/2, then you don't see anything. So you can at a single scale, you never see anything for a Ginzburg-Lardau energy because of the computation I made before. So that if you look at an annulus between epsilon to the gamma 1, gamma 2, this gives a contribution proportional to the gamma 2 minus gamma 1. So if you look at the scale epsilon to some lambda, this is you can put this in a very small annulus, or small in respect to the scalings, and you don't see anything.
Mm-hmm.
So somehow, in a sense, it's exactly this. One would say, okay, if delta is something, or if epsilon is something, fixed a priori, depending also only on the geometry, you see one thing or another. That's the usual homogenization, separation of scale. Here, you never separate the scales. You always, except in the cases lambda equals 0, 1, you always have a mixtures of the two behaviors.
Okay, so I do not continue because of course you are right. Okay, I would like to continue, but I think I'm the only one interested in this discussion.
We can continue privately.
So we can, after the end of the talk, which will be now if nobody asks again a question. No question. We stop.
Can I ask a question, François?
Yeah, of course.
Okay.
Hello.
I would be interested in a problem where you have a kind of infinite cylinder, and let's say at x equals 0, for instance, you have in kind of one dimension your homogenization problem, but it's not filling the whole domain. So the domain would be infinite in one direction, finite in the other. And I would put my homogenization problem only in the y-axis, for instance, for a finite 1D dimension. I don't know if it's clear what I'm saying.
Not
really. Okay.
So we are in 3 dimensions.
Instead of filling my domain with your homogenization problem, I would like to put it in a kind of thin strip in some sense. That is
two-dimensional strip.
Yes, for instance.
Okay. Mm-hmm.
And from the physics problem I'm interested in, there are cases where you can have vortices, homogenized vortices, and some cases where it could lead to a soliton. Because actually the 0 would be everywhere, so it leads to a kind of modica mortula solution where you have your homogenization, you get 0 everywhere, more or less. Do you think that your techniques could lead to distinguishes between these two cases?
I don't know, really. That's interesting, but I really. I would love to see the problem, but at this level of detail, I'm not able.
Okay, thank you.
Okay.
Thank you.
So thank you, Amandine, for your question. Everybody else? Another question? So if we do not have another question, let's thank Andrea again.
Thank you.